Hello, my name is Jaymie Bourdeau, and today we'll be talking about the Rayleigh Criterion. The Rayleigh Criterion is very interesting because it helps us understand why, at far distances, two light sources merge into one. For instance, as we drive on the freeway, all the oncoming traffic cars may look like motorcycles because their headlights blur into one. We don't know if it's a car or a motorcycle or a moped or what's coming towards us until we move towards the source or if the source moves towards us. The definition of the Rayleigh Criterion is the minimum separation or the minimum angle of separation between two light sources that may be resolved or distinguishable in two distinct images. And this definition is a lot, however, we will fully understand it by the end of this slide. Before we dive in, I'd like to review some essential concepts that will help in grasping the Rayleigh Criterion, starting with light characteristics. As we know, light acts as a ray when it interacts with materials larger than its wavelength. Conversely, it acts as a wave when it passes through or interacts with an opening that is the same size and or smaller than its wavelength. When we're dealing with the Rayleigh Criterion, think of light as a wave. The next thing we'll talk about is the diffraction pattern. All waves diffract or bend as they pass through an opening or an obstacle. This image to the right is true diffraction, as the wavelength of the wavelength of the light is equal to the opening length. Therefore, it bends and is more circulature as it passes through. When we're using the Rayleigh Criterion, we're using two light sources and we have a circular aperture. This is quite different when we're doing the single and double and multiple slits experiments, in that we use one light source and that they are slits instead of circular apertures. However, the light sources behave very much like they would in the other experiences and experiments. The biggest difference is the diffraction patterns they create. With the single slit and double slit, we see here that the red spots are the bright fringes. Those are the maximas, or where constructive wave interference happens. However, these dark spots that you can tiny see are where destructive wave interferences occur, and they are the minima. The same thing goes for this diffraction pattern. It looks different because of the aperture it's passing through, which can be confusing. However, the middle is still, and all the light spots are still maximas, and the dark spots are still destructive interference points. Now, tying that into resolution, the bending of light or diffraction limits the detail or resolution of an image and or light sources. So, the more diffraction, the harder it will be to see an object. The greater the overlap of diffraction patterns, the harder it will be to see anything. And here is our diffraction patterns in the right corner, and they're overlapping. And this slide kind of explains what's going on. So we have object 1, a light source, object 2, also a light source, and they are separated by an angle at some distance as they pass through, as the light passes through this circular aperture. And up here are the three overlappings, or three types of overlappings that can occur to create three distinct images, three distinct resolution images. So the three distinct resolution images are called well resolved, not resolved, and limitly resolved. The first one we'll talk about is the well resolved resolution pattern. Here, the central maximas are not overlapping, and that means that we can see two images distinctly. This also means that the angle alpha is large. As two light sources get closer to the circular aperture, the angle between the diffraction patterns gets larger. This is an example of a not well-resolved object. It's not resolved at all. This happens when the central maxima of one object's diffraction pattern overlaps the central maxima and the first minima to an extent that they are unable to be distinguished. As two light sources get farther away from the circular aperture, the angle between the diffraction patterns gets smaller. Alpha is very small, so there's blurring. and indistinguishable objects. The last example is when there is limited resolution. This happens when the central maxima of one diffraction pattern overlaps with the first minimum of the other. The two objects are just resolvable when this happens. As we can see here, we can kind of tell they're separate images, but it's kind of blurring. And there's the central maxima of one overlapping the first minima of the other. And this is just a quick slide of what I just said. A would be well resolved because the central maximas are not overlapping. B would be well resolved is limitly resolved, and that's when we use the Rayleigh criterion to figure out what this alpha might be. And this is not resolved at all. Here's the equation for the Rayleigh criterion, and that's how we find the angle. D, or B in some books, stands for the diameter of the aperture. Lambda is for wavelength, and 1.22 is a number derived by the basal function. This angle is where the first minimum is in relation to the central maxima, so that the two objects are just resolvable if they're separated by this angle. Now I want to talk a little bit more about the angle here, the angle theta. So this angle is sometimes called the angle of separation. Although the angle of separation is conceptually equivalent to just a plane-on angle, we call it the angle of separation to suggest that there is a linear distance between the objects, which leads us to our next slide, the applications of Rayleigh criterion. We can use a Rayleigh criterion to figure out how close something needs to be in order to see it, whether we're using an aperture of a lens or eye. I would do an example of this, but no one likes when our physics professor does it, so I will not myself. But if you want to know, message me and I can show you some stuff. Additionally, we use it to help us make telescopes, microscopes, and even to test the human eye. Thank you for listening. If you have any questions, please comment below.